Hello, dear listeners. We are pleased to welcome you to the new episode of NU SciPod, a podcast that provides you with expert knowledge and research in biology, chemistry, and medicine. SciPod is for students, researchers, and for anyone with a curious mind, offering clear explanation of complex topics to inspire and engage listeners. My name is Bek Mustafa Alisher, and I am the second year student at NUSOM Medical Sciences.
And my name is Amanbek Turgan. I'm first year life sciences master student here at Nazarbayev University. And today we're having a special guest, actually, the Dean of the School of Sciences and Humanities here at Nazarbayev University, Professor Gonzalo Hortelano. He went on a long journey prior to joining NU as a full professor in 2012 and becoming the chair of biology department in 2015. And now he's the Dean of SSH. Apart from his professional positions, Dr. Hortelano is also an outstanding researcher in cell encapsulation, immunomodulation, and nanotechnologies. He has studied the effective ways of delivering therapeutics to treat various diseases such as hemophilia, osteoporosis, and COVID-19.
Today, we are going to take a closer look at Dr. Hartalan's professional life and cover the topic of effective treatment delivery through cell encapsulation. Cell encapsulation is like a mini protective bubble that holds cells in a safe environment where they can function while being shielded from external conditions. So, enjoy and learn something new with us. Hello, Professor. We are very pleased to have you here. How is your day going?
It's going excellent, thank you. I'm very pleased to be here with you.
Thank you as well. Can you briefly tell us about your journey into biology? What specifically made you choose this field?
Well, this journey goes back a long, long way because I've been around for a long time as well. But I am naturally curious like many of the student minds today. And to be honest, I could have actually been just as happy being an engineer or a geologist. But I really liked to know how things work. And so, I remember I was 7 or so, and one day I had a headache, and my mom gave me an aspirin. That's in those days. And then I thought, how do doctors know that the aspirin will go to reduce my headache? And so this actually kept me thinking about just common things, but always related to my body. And so that actually sort of started my curiosity. This is about biology, yes.
That's very interesting. You obtained your degrees in Spain, South Africa, and Australia. You basically went around the world before coming here. Did you notice any maybe peculiarities in these countries in terms of research and mindset? And basically, what led you to Kazakhstan, to NU?
That's a very good question. So again, I have to go back to the beginning. So I did my undergraduate degree in biology in Spain, my native city, Bilbao. And but I was always interested in how science was done outside Spain. So this is what we know here, but I want to see other ways of teaching science and doing science. So from very beginning, I knew that I wanted to do my graduate studies abroad. So I basically applied. These are the days before internet, by the way. So I had to write letters and use a typewriter and those kind of things. So anyway, I did by chance, I ended up contacting a professor, Australian, who just came from Cambridge University and was going to South Africa, to Johannesburg. And even though my idea was to go to the United States, she crossed my path and said, if you want to come, I'll give you a scholarship and come over. And I said, okay, let's visit the country. So I went to South Africa. It was actually very well developed, which was very interesting. And then at the end of my master's, she said, I'm going back home to Australia. Would you like to come with me? All this with my wife, who is also a biologist, by the way. And so I said, okay, why not? So we went to Australia. So I did my PhD in Australia. Now, this was in a very different field. I studied, interested in microbes and microbiology because they are little living machines that can do anything you ask them to do. So I was very interested in that and in genetics. And so I did my graduate study working on a bacterium that causes a disease in citrus trees, oranges and lemons. And so that was fun, that was nice. I developed techniques and I advanced, but I wanted to move into human genetics and treat humans. And so I did decided to do my postdoctoral work in North America in human genetics. So I spoke to a number of people in North America, and then I had a few offers to do my postdoctoral work, and eventually decided to go to Canada to do my postdoctoral work because they were working on gene therapy. Gene therapy is how to use genes as a drug, as a therapy. This is a very advanced way, and rather than use drugs, then use DNA, then use genes to actually allow the patient to cure him or herself. So I thought that was the latest in medicine, and I wanted to be part of that. So I went to Canada, and then as a postdoc, but shortly after that, they offered me a faculty position, so I stayed in Canada. I was there for a long time. And before you mention about hemophilia, yes, I used hemophilia as a model. But I'm interested in how to deliver genes, how to deliver cells, how to deliver drugs. So developing new delivery systems that could allow to solve problems that today are very difficult to treat. So today we can use viruses to deliver genes, and the Sputnik vaccine is an example of that. And it works fine, but it works fine to produce an immune response. And this is fine as a vaccine, but if you want to treat hemophilia, which is a lifelong disease, you'll develop an immune response that you really don't want. So we have to develop specific treatments for specific questions, specific diseases, specific treatment and applications. So that is how I sort of came to work on new delivery systems. And the idea is that you say, if I give you my cells, you probably reject them because they're not yours. Your body will see them as foreign and they will fight. So it will not be very effective. You can do that with your son, with your sibling, within the family, but it's not easy. Not easy to develop a treatment that would be applicable to thousands or hundreds of thousands of people. So what we do is we cover the cells with a polymer that's biocompatible, so the body is okay with it. And that means that I can actually give you my cells, or you can give me yours, and that will be all right. So it started to develop new ways to be able to deliver genes, then to deliver cells, and to deliver drugs in a slightly different way, so that we could find applications to new problems.
That's a very complete answer, not only about your journey, but as well as topic and kind of journey of your interest in research. That was very informative. Thank you.
I'm kind of curious that you like basically were driven by your interests, not like the places you like. You have some interest that you're like maybe want to study this and that, and then you go search for a place where this is like the most well-developed thing where you want to go. And you mentioned that you were like a professor in Canada, and when you came here, you became the dean of the school.
Not initially.
Not initially.
Not
so
initially.
I wanted to ask, what primarily motivated you to take on this role?
Yes, yeah. So I had been teaching in Canada at McMaster University for 20 years, and so everything was fine. And then the Faculty of Health Sciences, where I taught, was ranked number 14 in the world. It was very good. And so, but I felt at that point that every year was the same as the previous year. And so I, over the years, I received offers to go and teach in the United States or go back to Spain, go to, exotic places like the Caribbean. But it was not attractive. Now, when I was asked to come here, then I met President Katsu, and I met a number of people, and then they shared the ambition of the project. It was a very new project. The ambition of the project was the most attractive thing for me, and being able to participate in such a project. So I decided to give it a try. I went back to my wife, and I said I'm interested. So I decided to take 1 year leave of absence, and see and take a look, a closer look. So I came here, took 1 year, and then I extended that to 2 years. And then after the 2 years, in Canada, they told me to make up my mind, either to go back to Canada or stay in Kazakhstan. And then I decided to stay in Kazakhstan. I met students like you, and the quality was exceptional. The ambition, and the ability to contribute to build something from scratch was very appealing to me. So I decided to stay, and I'm very happy because I've been here for 13 years now, almost 12 years.
We're also happy
So
to have you here.
so becoming a dean was rather recent. So it's about 3 years ago that the provost called me, and the previous dean was living in you, and so suggested that I might actually consider. And then I was a bit shocked, but I guess I love challenges. And it was a big challenge, but I don't shy away from challenges. So I decided, okay, if the university needs me in this position, let's give it a try. And here I am.
Okay.
But I'm not going to leave research because of that. So my mind keeps moving, and I keep having ideas. I love teaching, you know that.
Yes, I know that.
And so I decide I only teach one course per semester, and I still have my projects. So I'm very happy.
You're kind of predicting the next question that we are like going to ask is like that's a question that is like logical follow-up of you being a dean. We are also curious how it feels to be both a dean and a researcher. Does it complicate your research, or does it benefit it?
No, well, I don't think it sort of affects much. But being able to continue teaching and continue doing research allows me to have a better perspective on the school, on what students do, what students need, how they change over time. And on the other side, the faculty. We ask faculty to do research, to engage in research and in exceptional research. We ask them to take students in the projects. So it allows me to understand better what it means to ask students to do research and study, and faculty to do the same thing. So from that perspective is beneficial.
Mm. Our university is now ranked by globally known ranking system Times Higher Education as the top one research university in Central Asia and the top 30% among world research universities. It's such an incredible milestone that we have achieved, and it was obviously not easy. What are your thoughts on the initiatives that may have contributed to that? Maybe you can elaborate more on the path that lead us to this.
Yes, actually, this is an incredible journey, and the THE or also mentioned that NU deserves a case study because it's a very very unique case. Now, if you ask different people, will give you different answers. But from my perspective, we have the ingredients to make a successful university. One, the raw materials. The students are amazing. The students are not amazing, they are second to none. So there are students that go anywhere in the world, top places, and they are received exceptionally well. They write to me and say, "Do you have more like them?" I said, "Yes, we do." So the students are very good. If the students were not motivated, not good, it would not be as possible. Then we have the faculty. The faculty all come like me from the top 100 universities in the world. So it means they know what it means to be in the top universities in the world. And it's not that they imagine, they have been there. So that is the second ingredient. Also being 2/3 of the faculty internationals allows the students to get this global perspective on how different people in different places live, and even the culture, if somehow it transpires. So they get a multicultural environment that is very useful, in my opinion. Then we have infrastructure. We have infrastructure that is second to none. We just recently had a conference, and a top one of the speakers, he's a member of the U.S. Academy of Science, member of the U.S. Academy of Medicine, member of U.S. Academy of Engineering, just about everything. And he said, I was blown away. Astana is clean, Astana is beautiful city. The university has infrastructure that's similar to the best universities in North America. So basically, the infrastructure that we have, not that I say, but by top people, is very, very good and competitive. Means that you go to other universities and the academic side is not very different. It's comparable. And of course, we have been blessed with this government support for years. They believed in this institution, and they considered that it would be important for Kazakhstan. And so without that generous funding, it would not have been possible also. And we have staff that is very, very good. They are committed, very well trained, better than in North America. And so they all the pieces come together in a very exciting, fast-paced university.
Wow, that was a really. You kind of elaborated on the cuisine of the best university in Central Asia. That was very useful information for us and dear listeners, I guess.
Let me add that even though we are in the top 500, in fact, I believe that in fact we are better than that. And we are not, because 30% of the score is reputation. And we still don't have the reputation because we are so new. But in fact, we stand in quality higher than that. That's my perception.
I see. So we still have some room for expansion and improvements, actually, to become higher in this ranking. And I agree with that. I think, as people say, success is not like linear thing. It's very complicated, and I think a lot of our staff as students have put a lot to contribute to that, actually, overall. I think here we'd like to switch up from the general questions, from personal questions, to the more like research-oriented, especially about your research, Dr. Hortelano. So your research is centered around genetic diseases, prominent one being the hemophilia. So for our viewers, this genetic disease is caused by mutation in one of the genes responsible for clotting factors, which prevents excessive bleeding in human bodies. So as a result, hemophilia makes a person prone to spontaneous and excessive bleeding, and thus it's very life-threatening. So could you please tell us what are the standard ways for treatment of this disease and how effective they are?
Yes, so as I said earlier, it has been a good model for me while I was in Canada. Now, hemophilia is a bleeding disease, and it actually means affiliation with blood. So, and it is simple. If you just make a cut, blood comes out. Now, in most cases, when you don't have hemophilia, then you have a way, the clotting system, that makes a plug to actually stop the bleeding. It's combined with cells, combined with factors that you were referring to earlier. So in the case of hemophiliacs, they have a mutation in the genes, and so they cannot produce functional product. That means that they cannot stop the bleeding. They cannot make a plug or they clot. And so they bleed. They could bleed to death, actually. And so the treatment for that traditionally has been either blood from donations. That's why transfusions and blood donation is so important, to be able to share. So the clotting factors are prepared from blood donors and then given as transfusions as blood transfusions to those hemophiliacs. So this has been a traditional one since the 1980s, when genetic engineering came to the picture. Then those products can be made by genetic engineering. In other words, we genetically engineer a bacteria, for instance, to produce a protein, or we can do the same thing with mammalian cells, but in a laboratory or in some kind of bioreactor. And so that can be done, and then purify the factors, and the factors can be delivered. And the advantage of this is that you avoid the possibility that during blood transfusions you may have, at least in the old days, have some viral infections, and you might actually provide some unwanted elements. Again, this is more like from the 40 years ago, when the screening mechanisms of blood were not that high. Now blood is very, very safe. So I think I encourage every one of you. I've been a blood donor since I turned 18, and I've donated in many countries. And so now it is very safe. But these are the two main strategies. But whatever the strategy you use, because it's a lifelong disease, those products over time, over days actually, they disappear. They degrade in the body, and so you need more. That means that hemophiliacs need to get injections maybe every 2-3 days directly in the vein. And that is not only annoying for hemophiliacs, but it's also a risky source of maybe infections or problems of other kind. So a new way to treat hemophilia is being sought, particularly by patients. I spoke to many patients, and they cannot wait to get a better system. Can you give me one treatment that will cure hemophilia? So gene therapy was this, at least they imagine that it will be such a treatment. So imagine you just have an injection that's it, will just sort of cure hemophilia. And from the very beginning, we looked to do that. Now, it is not as simple. And this is actually a common case when, remember, when the gene for cystic fibrosis, which is the most common genetic disease, was cloned, and near McMaster, I know the Lapji Choi who cloned it, and everybody thought that in 2 years there will be gene therapy, because all you had to do is sort of sniff the gene, and that was it. But even today, 30-40 years later, we still cannot do it well. So nothing is as simple as it initially imagined. And so we need to understand that it might be good for certain diseases, and for instance, it's very, very good for cancer. It's excellent for vaccines. It was proven in with Sputnik as a vaccine for COVID. But for other diseases, it's still not ideal. So we need to come up with new ways, new mechanisms And again, I started with working on the hemophilia as a model, but I have actually published, as you mentioned, in different things, as when I've come up with ideas of, okay, maybe this strategy could help this other disease, so let's try it.
Mhm.
I always say, you have what do you want, a Ferrari or a Land Rover? And I said, well, depends. If I'm going on the highway, a Ferrari. If I'm going up in the mountain, I want to take a Land Rover.
Yeah, so it all depends, and it's all like very situational. Like for some things you would like to have different kind of treatments, and for other they are also different. And there is no like universal treatment for all diseases actually. Yeah, unfortunately.
Do you know? It's kind of, you mentioned like we were aiming just to cure hemophilia by making an injection. To be honest, it sounds like a magic. Even if you made that thought exactly like 30 or 40 years ago, and are we really like not making any progress in 30 or 40 years? Because it's still, you mentioned that it is still not easy to do, even in such amount of time.
No, we are making progress. We are making very good progress. There are very smart people working on it. Um, Initially, they used viruses like Sputnik, but again, they face the immune response. They came with newer viruses that are not as responsive by the immune system. But I remember telling the investigator who came up with it, I said, but you need to be careful with the immune system response. I said, no, 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 not with this virus. I said, okay. But time told us that the immune response has to be considered. I mean, over our evolution, viruses have developed the way to get into our cells.
Mm-hmm.
And for survival, basically, for the viral survival, the virus needs a cell, a mammalian cell, to survive. But at the same time, our immune system, our bodies, have responded by evolving in a similar way to catch up with the viruses. Now, if we didn't, we would be dead as a species, and we are not. So we are sick for a week, but after that, our immune system basically takes over and stops the infection. So it is a constant battle, tug of war between viruses and body, our immune system, more in particular. So we need to understand this if we are going to be able to develop new ways. So, and that brings me to the interdisciplinary nature of research and how important that is.
So our immune system is basically what saves us and also prevents us from making some like very, how can I say, it might sound like but like bold moves from like in research and therapeutic approaches to do to make some treatments against such diseases. So but however, we have some ways to overcome this immune response trigger by our um, by our bodies via probably cell encapsulation. Yes. So could you please describe how exactly does the cell encapsulation work? What does it consist of, and what are you trying to do with that?
Yeah. So we initially use cell encapsulation, as I mentioned earlier, as a way to be able to use a particular cell and introduce it after modification so that it will be producing a therapeutic product that is needed by the patient, just to not having to do the same exercise for every patient. In other words, we have what we call the universal cell that we could, if encapsulated, it will be isolated physically from the cells of the immune system of the patient. Therefore, they would not be killed. And so that was the idea. Now, what happened is that the the cells encapsulated themselves produce many other things, not only the therapeutic products. And so if they are also contribute to the immune response. And so this is one side. The other side is that the viruses were developing in a way that could be an alternative, acceptable alternative to the current treatment. Now, today there are a few patients treated with gene therapy, hemophiliacs, and this is fine, but I don't think all hemophiliacs will benefit from this. They will still be needing something different, and there are many other things we can do. So, for instance, being able to modify or edit or change the sequence of the DNA in the genes so that now it will not be mutated, and we have mechanisms like CRISPR-Cas that can do that. It's some kind of molecular scissors that you can go inside the cell, change the sequence, and now it's no longer mutation, and the cell is able to produce functional therapeutic product. So in other words, basically allowing the patient to cure himself or herself. That's the future. It's still done maybe in animals, but that might be a feasible outcome in the future.
It still requires like constant injections, right? Because they do not last forever in our bodies, or do they?
Well, if you manage to change the DNA in cells, then it would be potentially one treatment, and that's it. Now, for the encapsulated cells, yes, that will be it could be a long while, not every couple of days, but we have had microcapsules with cells for months, and this is fine. Now what we use them for, we have a project where we use them as factories for therapeutic products that are either very difficult or very expensive to produce. So, for instance, we have many drugs for cancer, monoclonal antibodies. Monoclonal antibodies that will target cancer cells. So it's like little molecules that target cancer cells, and then the immune system can eliminate them. So they are used in the clinic, but they are very, very expensive. There are some that cost $500,000 per patient per year. And so, because the purification is very costly, it's complicated. So our idea is, well, if we engineer cells and put them inside a capsule, maybe they can produce monoclonals for us. So this is a new application of encapsulated cells that we use now.
Sometimes, yeah, I agree, because there's limitations for any method. For example, we are talking about the monoclonal antibodies. It's kind of, for example, that's the matter of money, because it's quite expensive for each patient to get that treatment. And what are the specific limitations of the cell encapsulation method, and why is it still not used on humans? We mentioned that it is used on animals, but as far as we are concerned, on humans, it is still not that popular yet, if I can say like that.
Well, I think the complexity of injecting into a patient cells that are genetically engineered, together with a chemical polymer, that it's a far more complicated formulation than simply adding a chemical that is just purified in a pharmaceutical industry. But I think there is a lot of avenues, lots of avenues. I mean, I keep having ideas all the time, but about 3 years ago, there was a article in a top journal in Science made by about 5 different departments in Stanford in the US, where they took liquid from the brain of young mice and they put it in the brain. We have not only blood, but we also have some cerebrospinal fluid stemming from the produced in the brain and then going back into the spine and then absorbed. Now, they did manage to put that liquid in an older mice. And what do you know? Older mice gain cognition. They became younger, and not only younger in terms of mobility, but they actually gained cognition. They had memory. And so they looked at why that was, and they looked at whether the cells in different parts of the brain had changed, which genes were activated and which genes were inhibited. Not all the genes in the cell are active or silent at any one time. So this is very important. And then eventually they came up with one particular protein that was key. And so when they injected simply that protein in older mice, the older mice regain cognition. And so the problem is, how are we going to deliver that? And so the capsules, the encapsulated cells, can and have been injected in the spine of patients with cancer. So it is possible to do that, engineer cells to basically produce that protein and then have it delivered to the brain to regain cognition in Alzheimer's disease or older patients, for instance. So you need to pick the application very carefully. It will not be useful for every medical condition, but you need to be very specific as to what are the needs of that particular disease, what are the needs of that particular patient, and then find what is the best technology to use.
So, however, technologies give us like these additional tools that we could utilize to come up with new ideas on how to treat different diseases. And as you said, we can encapsulate not only cells but also like proteins and maybe perhaps even other stuff such as DNA, which is one of your topic of research, actually, oral delivering of DNA by encapsulation. And what made you consider studying DNA encapsulation?
Yes. So, well, it started because I was invited to a seminar series at Johns Hopkins when I was in Canada. And I went and gave a talk. And then, typically you go, you give your talk, and then you visit the department and you have talks with other professors. And so there was a professor in chemical engineering who was starting to work on this. And so I became very interested. The reason is, if you receive any insult, for instance, you cut yourself, or maybe you scratch against the wall, immediately your skin becomes red, and becomes red as a response. This is an insult, and so immediately, in case you have any break of the skin, the immune cells go there. The blood vessels open up, allow permeability and blood cells flowing to the site of injury. And so they are ready for anything from the outside that will be there. So this poses a big problem when you're trying to inject anything that's foreign. It will be received as in the context of danger. And so never mind if you just poke a needle, that's already injury. And immediately you will have that. So, however, we eat foreign stuff all the time. Actually, that's all the thing we eat. And yet, most people are fine. Why is that? Well, because we need food for energy, for survival. That's, we are not photosynthetic. We don't have green hair. So we need to eat. And so we need to eat, we need to get energy from the outside. We need to develop the system to decide, it's from the outside, but it's through the intestine. So we are good. Don't attack it. So I saw that as a way to be able to bypass the typical immune response. And so that's how I started. And in fact, now we're working on this. So the idea is to deliver genes, not through injection, not through viruses, but simply eaten. It's some kind of pill, gene pill. The problem is that we also have defenses against that for good reason. And so in the stomach, the very acidic condition of the stomach will degrade DNA. So we had to protect it. We have to formulate it in a way that is not degraded. And we did that. And then once we do that, then the DNA keeps going from the stomach into the intestine and is taken up by cells in the intestine, just like it does when you eat vegetable. And then the cells in the lining the intestine will take that DNA and will express it. That's what they do. And so the idea is that the DNA that you eat is sending the message to produce a therapeutic product. Now those cells in the intestine will produce it, and that goes on to the body. And particularly the benefit is in modulating, either to say don't attack it. You could also say attack it. We also learn how to do that, but generally is to avoid immune responses. So we have a project now to do that for diabetes. Can we eliminate or reduce the immune response against insulin or insulin producing cells? And so this is a way by basically teaching the immune system that this is okay, you should not fight it. So as a way to somehow modulate or not to attack something, a therapeutic product that otherwise would be. So again, I saw the need, and I thought that this could be a good way to bypass the problem.
So kind of we are working with the human materials as well, because if you want to apply some method, some drug to people, usually we are working with human samples, and it requires a lot of responsibility, and it raises an ethical issues. Considering the uptake of foreign DNA by human cells when we are taking the drug by this method, what ethical issues may arise, in your
Yeah.
opinion?
No, this is good. This is a very good question, an important question, and there are always sort of concerns. There are always risks. Of course, we try to use the lowest risk, but I don't think the risk will be zero.
Hmm.
So what we do is try and every jurisdiction will do that. So look at in a balance, put in a balance the benefits, the benefits that potentially you could provide patients if you give them this treatment, versus what will happen if you don't. What is the current treatment? What is the alternative? In the case of hemophilia, for instance, we have a treatment. The bar is very high. In other words, whatever new method has to be at least as safe as it is today, and more convenient, maybe more economic. That is fine. In the case of cancer, for instance, particularly in some aggressive cancers, then unless you do something quickly, basically death is immediate. And so depending on the condition, you see that the same treatment is either acceptable or not acceptable. So we always have to have in mind the ethical consideration. So who is going to receive this? What is the potential benefit to them? And two, what are the potential risks? And so, for instance, in the case of DNA nanoparticles that we develop orally, so the gene pills, then it would be more effective if we use, for instance, viruses. but we opted not to do that because of the potential for the viruses to get inside the cell, integrate or basically plug themselves, glue themselves to the genome, and will stay there forever. And so we try to avoid that. So rather, I said, it's much easier just to take a pill every couple of days, but to avoid this danger. So it's a very important question, something we need to consider. For instance, in terms of encapsulation, it is good to produce monoclonals, but I understand that, and in the case of aggressive cancers, it might be advisable to inject such a encapsulated cells, but we're looking for a safer method. So we are trying to develop some devices that stay outside, a bit like some kind of nicotine patch, something that could be on the skin, and basically it could be delivering the same product. And if once you don't want them anymore, just lift them, and that's it. So we're looking for safer mechanisms all the time as technology comes, but we need to use interdisciplinary technology, engineering, chemistry,
Yes.
biology.
So there is always a new methods like coming in, technological advances, and of course people that are going to be treated by these new methods, they can probably overreact to new things because many people, I guess, they perceive the novelties differently. So how do you think, is there any possible overreaction from the patients when you are trying to introduce something new and maybe unknown to them?
Yes, of course. For starters, we are different. When we treat mice, they are basically identical. People are not. It's very easy to see that. That we are different. As we are all the same species, well, human, but we have different DNA. We have different immune system, so we are different in many ways. That has to be taken into account. And now there are mechanisms to be able to somehow find a signature. Imagine the barcode that you find when you buy anything at a store in Magnum. So that barcode will tell you exactly what that is. So imagine we can produce some kind of barcode for the immune system. And that would be special for me, but it will be able to understand. So personalized medicine will facilitate all this. But in addition to the technical way to develop a strategy that is good for a particular patient, which is a goal, it is the society implication of, no, we don't want this, either because there is mistrust in the government, either because there is mistrust on the treatment, and vaccination is an example. There has been a lot of mistrust that vaccine may lead to autism and things like that. Of course, there's no basis for that, but that is this is a concern. And how do you change that? Education and to explain what it is, and of course, I remember my neighbors in Canada have 4 children, and they don't believe in vaccines, for instance. And they were saying, my children have not been vaccinated, and they are fine. And I had to explain, yes, of course, that's because my children have been vaccinated. I have been vaccinated. Those neighbors have been vaccinated. 98% of all the people around you have been vaccinated. That is called herd immunity. And so you don't need to get 100% vaccination to get everybody protected. But understanding that, of course, there could be very, very rare cases of immune responses and adverse effect, for sure. But the absolute benefit to society way way outweighs the potential limits. And so, but education is the only way, data.
So yeah, basically education is like the most important thing when it comes to like general public's reaction to such novelties, to such innovations, and also education helps us to make some like predictions as well. And I'd like to ask you, as a professional, from your standpoint, how soon can you think cell and DNA encapsulation will become like a common treatment, common treatment method for like a variety of diseases which could be treated?
Well, I don't have a crystal ball, yes,
Yeah, none of us does.
but
We could make predictions.
I don't think that it will be a single method that will be used. It will not. Just like for a COVID vaccine, there are different strategies. Yes, the public will not know about them, but they are all very different. And so some are using only proteins, others use viruses like Sputnik, others uses mRNA. So they are all different technologies. They can all get the job done. Yes, and there are other ways, many others. So Kazakhstan has the inactivated viruses. So there are many things. So will cell encapsulation be useful for everything? No, I don't think so. It is a complex technology, and so I think you have to look for the right application that's going to be particularly suitable. Same with the DNA nanoparticles. I remember there was a student in biology here, and he came to me saying, she came to me and saying, my mom is sick, and there's a condition that basically you get inflammation of your bowel, of your gut, of your intestine, and it's problematic. So you need to reduce that inflammation. And then I immediately thought, well, I have something that can help your mom, but I cannot give it to you for ethical reasons, you know. So because we could encapsulate DNA that I had actually in the lab to not to produce inflammation, but anti-inflammation, to reduce the inflammation. That would be, and in fact, it has worked in other settings. So for that, it will be, I think very good, very easy. I think it will work very well. But will it be useful for every disease? No. It will be, you need to be very careful about the application. Just like I mentioned, a truck has its sort of purpose, a bus has its purpose, a Ferrari has its purpose, and a Toyota has its purpose.
Now I think we can proceed to the conclusion part of our podcast. I'm always trying to take a general conclusion. For me, I think the main conclusion was that the main quality for a researcher is a curiosity, because being curious is the nature of opening something new. If you are not curious, you are not opening something new. I think it's logically kind of coherent, but the most important thing that I mentioned from podcast, from talk with you, is like you can take an inspiration from simple things in life. For example, I really do not doubt that, of course, if I scratch my skin, it's getting red because there is a blood flow that is trying to open the. It's kind of a reaction to the outside danger. But when you are taking it inside just by eating the food, by like simple mechanism that we are doing every day and not thinking about it, eating food, and our immune system is not responding to it, then thinking like, okay, I can make a drug that could be like that could work like eating food. It will be regular and immune system would not respond. And as well, you mentioned a lot of examples that were like from our simple life, because every one of us are buying products in barcodes, and that's also one of the kind that, for example, specifies the specificity and for the methods of drug delivery or even treatment. So it's important to have an inspiration from simple things in life, and the most important thing is to be able to correlate these simple things with such complex topics in science. That was the most important conclusion for me, I guess. And for you?
Well, I personally want to thank Dr. Hortelano for coming and for sharing such brilliant insights on his personal life, on the science, on the research, the cell encapsulation, the methods, their application for me were the most, I think, interesting part in this conversation. I really like that there is like, I think it's very obvious idea, but sometimes it just doesn't come to your mind that there is no like singular treatment. You have to like think broadly. You have to improvise. You have to think to find some new ways to adapt, to overcome. And the stories that you have shared with us, I think they actually motivated me to study more, to learn more, to like go and do some significant research to help to benefit to us all. And would like to also hear your opinion on this.
Yeah, so the curiosity is a key factor. I think curiosity is the ability to ask questions that not afraid that they're too simple. There's no such thing as a too simple question. Said, why is this that way? And what if, and it could be a too simple question, but if you're able to ask questions, eventually you'll be able to find answers as well. Second is that technology changes very rapidly, very rapidly. So for students, for those of you who are thinking of going into studies now, well, 10 years ago, 7 years ago, who had heard of artificial intelligence? Now, it's in every phone, every WhatsApp, it's everywhere, yes? And so every time you use the internet. So we need to be able to adapt to this new technology. Just like I mentioned that initially I typed my typewriter. I write my applications on a typewriter and then a computer and so on. But keeping up with technology, the technology changes so quickly that all our students today need to, and that should be probably the main goal, to become lifelong learners. So you get your degree, that's not enough. That's not the end of the road. It's just the beginning to continue. That should be part of your life. In other words, if you're curious, you will ask questions all the time, and you will keep up with what happens tomorrow and in 5 years, in 10 years, and then you will be a very valuable member of the community, which is the goal.
Yes, actually in Russian we have like the saying that goes like you live a century, you study a century. So
No.
you never stop like studying. You just continue. No, it's a process that actually never ends. Yes, I agree with you on that.
So I guess we're leading to end. So thank you for coming, for sharing such interesting information with us. I think it was quite interesting both for us and for our listeners as well.
Yes, so I hope you enjoyed it and learned something new from our podcast. So stay tuned and stay tuned for our next episode.
Thank you very much.